Hi there, I want to talk a little bit about Beer's Law to give you kind of an intro. We were just looking at this simulator with PhET Simulator, and you saw that if you pick something like a green color, if you look at the wavelength in the green light wavelength, it had a high transmittance. That's how you see the green color. It transmits the green light through, and that's how we see it with our eyes. Rather, if you would move it to something like the blue light, you see the blue light has a really low transmittance. Most of it is getting absorbed. And so what I want to talk about here real quick is when the atoms absorb that energy, that wavelength of the blue light, what are they doing with it? And then two, how can we use this information to help us know something about the solution? So let's take a side step to here. Now if I lose you here, it's okay. It's really okay if I lose you. But I want to talk real quick. So you're shooting this different colored light at the compound. And then once you shoot the light at the compound, what does it do with it? Okay, so we have to get back to the basics. A compound is when you have one atom and another atom, and they come together and they bond. So let's take a look at one atom. That's this off-by diagram for one atom. And let's say you're going to bond it to another one. You can see I made some really big off-by diagrams. It goes all the way to 6D, 5F. So these are two atoms, and when they come together, atom 1, atom 2, they're going to merge together like this. So let's take the most simple atom, like hydrogen. Hydrogen is 1s, and another hydrogen is another 1s, and these two 1s orbitals, which are like lines where the off-by diagrams are, actually kind of merge into this new kind of weird thing. Boop, like this. So now, here's one hydrogen's electron, and here's another hydrogen's electron, and they have now merged together, and this is H2, the compound. And what happens is, you've got this compound, so the electrons sit right here. This is called the bonding, the sigma bonding. This is called anti-bonding. If you shoot some light at it, the right wavelength of energy, these electrons that sit at the bottom will absorb it, and then live up here in this anti-bonding region, and then eventually they do release it to go back to their ground state. But do you see how this is just like a tiny little jump? This tiny little jump doesn't produce colored light as it spits out. It's just producing and showing us our absorbance spectrum. So that would give us something like this. So let's go back to our part here. So if I've got a green solution here, and if I want to look at it at a wavelength of the lowest wavelength from here all the way, see how the transmittance is changing over time as I move it toward the red? So I just took like a whole spectrum of it. Now that's what I'm going to do for that iron chloride to look at. Iron chloride is kind of this rarest kind of solution, but not exactly. So it's kind of like I'm taking from this wavelength, the low one, all the way to a high wavelength. And when I take its absorbance every single time I'm looking at it, I get this sort of graph. You can see that my absorbance went up and my absorbance went down. Now the key thing to know about this is that it changes over each wavelength, which we looked at, because depending on the color of the solution, it will absorb or transmit certain colors. The other key thing to look at here, and something you do need to know, is about concentration. So take a look at this thing on the left. Think about the curve we just saw, this one here, and pretend that curve is this one right here, the bottom one. Whoop, whoop. Now if you make the solution even more concentrated, it'll go whoop, whoop, because the higher the concentration, the more it can absorb. It's got more electrons that can do the little whoop and move back down. So as your concentration of the solution gets higher, your absorbance gets higher, which is what I can see over here. As my concentration gets higher, my absorbance gets higher. This graph on the right is our Beer's Law graph, which is what you're going to really look at next. And you can tell us the concentration of any unknown solution, which is what I'm doing for dilutions. The key idea I want you to get from this video is two things. One, as I look at absorbance, it changes per wavelength based on transmittance and absorbance based on the color. Two, as concentration increases, the amount of absorbance can increase. And three, if I wanted to know the concentration of some sort of iron chloride solution, assuming this is its spectrum, would I want to look down here as that volume changes, as that concentration changes? No. Do you see how these changes really are very minimal? As the concentration changes, my absorbance doesn't really change. And over here too, it's like, meh. If you really want to look at the concentration and how that has changed, you want to look at where it's got its highest absorbance spot. So when I'm going to do this FeCl3 for your solutions, I'm looking at a wavelength at about 450. That's its peak. So if I had something that's more concentrated, it would make a whoa, really high graph, and I'd be able to see that change. If I pick something at like 300 nanometers, I'm not going to be able to see that kind of concentration change because it doesn't really do a whole lot. As you can see right here, it still sticks kind of low. So those are the three key parts. Concentration changes over time. You want to look at the big whoopties, and you're going to be looking at the Beer's Law graph a little bit more.